So in our last discussion, we were discussing basic thermodynamics because after going through Petitfort maps and Villa's structure maps, we realized that the interatomic interactions play a major role in determining the structure and properties of the materials. So then the approach was to look into formation enthalpy and entropy calculations and look a little bit into basic thermodynamics, because that was one method by which one could rapidly calculate reasonably accurate potentials in terms of enthalpy or free energy, which would become predictors of phase stability. Now, once you are able to calculate these things, you are also able to calculate something known as phase diagrams. Now, phase diagrams are extremely important in material science, and basically, as far as we are concerned, we will be looking at phase diagrams of materials at constant pressure, and usually that's going to be 1 atmosphere pressure. So if you look at a binary AB system, you will basically be having a phase diagram that looks like this. On the x-axis, you have the amount of one element, and on the y-axis, you have a temperature. And within this, you will be seeing all of this type of lines, which will give you an indication of how the different phases would be coexisting. So we will look a little bit more into that. And so before we dive into the phase diagram, we just want to get a few definitions which should be very clear. So what is a phase? A phase is something which is chemically homogeneous and mechanically separable. But the jargons apart, really what we are talking about is this would be some region. So for example, a region like this where the crystal structure is not changing and the lattice parameters are varying continuously. And if you look at the chemical compositions, you are having proper mixing over here. Now, what happens if you have a compound? In that compound, the width of the phase in terms of the composition is going to be very small, and you will be having a proper ordered structure most of the times if we are talking about ordered stoichiometric compounds, and each atom will have a certain place to sit. So in that sense, that's also going to be chemically homogeneous. So in addition to phase, there are something that we call as components. So this is basically the smallest irreducible units which is taking part in this phase diagram. So in this case, the components are going to be A and B. Okay. So once we have an idea of phases and components, we can now start looking into the phase diagrams in a little bit more details. Now, those who actually have studied thermodynamics in other courses or have studied phase diagrams will also understand that there is one more factor coming into the place, which is the degrees of freedom. So we'll talk about degrees of freedom a little bit later, but having given the basic idea of what a phase is and what a component is, let us move forward. So the first thing you want to know is where can you actually find the phase diagram? Remember, everything that we are doing in this course with respect to the fundamentals of material science is going to have a couple of objectives. You should either be able to calculate features or descriptors, or you should know what you are looking for so that you can dive into the data and extract the data in a meaningful manner. So phase diagrams are wonderful repositories of data, very structured data. And this has been going on for a long time. ASM, the American Society of Metals, they actually publish a series of handbooks, and then this handbook volume number 3 is one that deals with alloy phase diagrams. So this is one place in which you can find the phase diagrams. And then if you are not looking at metallic materials, if you are looking at ceramics, for example, you have another beautiful repository of phase diagrams, which is maintained by the American Ceramic Society and NIST. And so they have this phase equilibria diagrams, and these are excellent resources for the phase diagrams of ceramics. So by and large, these phase diagrams are essentially, in some sense, you can say that they are creating a map of crystal structures. They tell you which phases can exist in equilibrium. Most of the phase diagram that you will see in these two repositories are equilibrium phase diagram. All right. So they will tell you which phases are existing in equilibrium, over what temperature range they are going to coexist in equilibrium, and so on. And why do these things matter? Because as you have a phase transformation, there's likely going to be a change in crystal structure. Not necessarily, but likely there's going to be a change in crystal structure. And then basically what's going to happen is, along with the structure, the properties of the material also change. So as you go from one phase to another, maybe by changing composition or maybe by changing the temperature, you might actually see a drastic change at the boundaries of the two phases. And so those would then start turning out to be the causes for nonlinear variations of properties of materials. So as we move forward and we try to predict the properties of materials, we must appreciate that there is going to be a significant amount of nonlinearity, and we should try and figure out from where this nonlinearity is actually coming in order to make better models. Now, to understand this equilibrium phase diagram, let us first understand what equilibrium is. Last time when we were discussing, we said that higher the energy, lower is the stability, and higher is the reactivity. And so this kind of provides a framework based on which you can start understanding what equilibrium is. So essentially, if you get to a situation where the system is not able to lower its energy any further, it is going to be in equilibrium. So now let us look at this in the context of different materials and systems. So supposing we have a binary system which is comprised of, let's say, two elements A and B, right? And supposing we have got a phase diagram between A and B which looks something like this. Okay, so now here you have got a bunch of phases. On the left hand side you have got alpha, which is a solid solution of B in A. On the right hand side you have got beta, which is a solid solution of A in B. And then above the melting temperatures of the alloy at relatively high temperatures, you've got a molten liquid, so that is only the liquid phase. Now between alpha and liquid you have a region where things are partly liquid and partly solid, so this is a liquid plus alpha phase field. Similarly, on the other side you will have a liquid plus beta phase field, and in between alpha and beta you will have a mixture of the alpha and beta phases. So you might be having a phase diagram like this. So if I look at, let us say, this particular composition and at this particular temperature, you will see that alpha and beta, they are coexisting together. So is there any way in which we can do these calculations? Is there any way by which we can know what composition of the alpha phase will be in equilibrium with what composition of the beta phase? And it turns out that there is actually a wonderful tool that we can use in order to do all of these calculations and get an idea of which phases are staying in equilibrium. This is really important because when you are trying to model multi-component materials and multi-phase materials, it is important to know which phases are in equilibrium, what are the composition of those phases, and how much fraction of that phase is there in equilibrium. So to do this, we use something called the free energy composition diagrams, or that's popularly also known as the GX diagrams. G stands for the Gibbs free energy and X stands for the composition. So these diagrams are always drawn at a particular temperature. And so basically what you do is you start plotting the free energy of the alpha phase. You start plotting the free energy of the beta phase. And because we are looking at a fairly low temperature, we are now not going to bother with the free energy of the liquid at this stage. So usually the free energy curves will have a curvature like this. Okay. And so now if you want to know where do you actually have equilibrium, all you do is you draw a common tangent between the free energy curves of alpha and beta. And so now what you have is 2 points which I am going to call as XA alpha and XB beta. So this tells you how much of what composition of alpha, and the composition is given in terms of fraction of A, is in equilibrium with what composition of beta, where I am using the composition as fraction of B. So why do we actually need to make this common tangent, and what are the implications? So essentially what we are trying to do is we are trying to lower the overall Gibbs free energy of the system. So if you consider a composition right over here, or let's actually choose a slightly different composition, which does not go through this point. We can come back to this a little later. So at this composition, phase beta is going to have a high free energy, and phase alpha with that composition is going to have a high free energy. But supposing the material now starts to decompose into two different phases instead of staying in single phase, what happens is the composition of alpha can change until it comes to this point, and the composition of beta can change until it comes to this point. And then what the straight line basically denotes is just a compositionally weighted free energy of alpha and beta. And so what you notice is the point on the straight line lies below the free energy of individually alpha or individually beta. So basically what this is saying is the system can go from one phase to two phase in order to lower its overall free energy. So how do we actually get this line? This line is essentially a common tangent, and so what that means is it's going to have a certain slope. So we can define the slope as mu, which is nothing but dou g over dou x, and this is something that we think of as the chemical potential. So the driver is to equate the chemical potential of both the phases. Now, the advantage of being able to plot this free energy composition diagrams is this will now tell you how the phase diagram is going to look. So for instance, supposing we have a situation which looks like this. Again, we are going to consider our AB system, and on the x-axis we have got the percentage of B, and then the y-axis is basically the Gibbs free energy. So supposing you have got a situation where your alpha phase Gibbs free energy goes something like this, and then the beta phase Gibbs free energy goes something like this. Let's call this G beta, and then the liquid free energy is a lot higher. So as we discussed, we find the equilibrium by drawing this common tangent, which we are going to call a Gibbs common tangent, and from here I can find out the compositions of the alpha phase and beta phase that are in equilibrium. Now these free energy composition diagrams are drawn at a certain temperature. So what that means is at this particular temperature I know how much of alpha is in equilibrium with how much of beta. And when I say how much, I'm basically talking about the composition. So similarly, you can make the Gibbs free energy composition diagrams at lots and lots of different temperatures and then find out the equilibrium points. So supposing your equilibrium points come out in this manner. So essentially what is now happening is you are starting to plot the lines of the phase diagram. As you go to higher and higher temperature, you will no longer be able to ignore the free energy of the liquid, because the free energy of the liquid will become fairly low, and therefore your free energy composition diagrams might start looking something like this. So you have the free energy of, let's redraw it a little better. You have the free energy of alpha, you've got the free energy of liquid, and then the free energy of beta. So this is G alpha, G beta, and then as the temperature goes higher, the liquid is also relatively stable, and you might be having a free energy of liquid that looks like this. So now you have this common tangent which is touching the G alpha curve, the G beta curve, and the G liquid curve. So this really means that this is a special situation where all of the three phases are in equilibrium. So the solid alpha, the solid beta, and the liquid. So as you plot these lines, you might actually find that when you join them, you start getting the complete phase diagram. So where you are now able to compute what the alpha phase field is, what the beta phase field is, and what the liquid phase field is. So by and large, what you really need to know is you need to calculate the value of G alpha, G beta, and this is where the discussions that we had last time is going to help you in doing those calculations. Now there are many different types of phase diagrams that you will see in case of materials. So instead of going over all of the phase diagrams, I'll just go over some of the common types not even all the types, but some of the common types. So the first type of phase diagram we are going to talk about is this isomorphous phase diagram. And as an example, I pick up this silicon germanium system. So why silicon germanium? Simply because these are actually fairly technologically relevant materials, because you can make semiconductors with them. So an isomorphous phase diagram is one in which you have complete solubility of silicon and germanium. Okay, complete solubility of both elements. And so that's why what you see is in this region below the solidus line, you have essentially a solid solution. So in case of an alloy, the alloy will not melt at a single temperature, it melts over a range of temperature. So supposing I take an alloy with this composition, it starts melting at this temperature. So the temperature at which the melting starts, that is a part of this liquidus curve. So liquidus curve, you can think of it as the locus of all of this onset melting temperatures. As you go and cool down further, you come to the point where the solidification process is complete, the freezing is complete, and that is the solidus curve. Okay, so here at the higher temperatures, you've got the liquid. In between the liquid and solidus, you've got a combination of liquid and solid, and then below the solid, you've got the solid solution. So since there is complete solid solubility of silicon and germanium, basically what you can understand is the phase is not changing. It is the same solid solution phase throughout. The crystal structure is not changing. Now, as far as the melting temperature is concerned, what you notice is if you try and simply take the average of silicon and germanium, compositionally weighted average, you will get a straight line that looks like this. But your melting temperature is not really given by this straight line. It is given as a combination of the liquidus and solidus curve, because the alloys don't melt at a single temperature, it starts melting over a range of temperature. Another one would be the eutectic phase diagram. This is a pretty common type of phase diagram, and we've been kind of using this type of phase diagram as an example. So here I'm taking the example of aluminum silicon alloy. Again, wonderful alloys with lots and lots of applications. So aluminum melts at fairly low temperatures, around 661 degrees centigrade, compared to silicon, which is probably around 14 degrees centigrade. So here you have the alpha solid solution phase. You hardly have any solubility of aluminum in silicon, so you don't really see anything over here. And so your phase fields are liquid, alpha, alpha plus liquid, liquid plus silicon, and over here you've got aluminum silicon. So in case of a eutectic phase diagram, basically what happens is a liquid cools down, and where you have the eutectic reaction, which is basically at this point, at the eutectic reaction, the liquid cools down to give you two different solids. So solid 1 and solid 2. So in this case, the liquid is cooling over here in order to give you alpha plus silicon. So this is basically your eutectic type of phase diagram. It has this type of reaction, this eutectic reaction, and that is what characterizes this type of phase diagram. Now, here you will notice that I am talking of a particular point where this eutectic reaction is occurring. And this brings us to this concept of invariant points in phase diagrams. So at this stage, we also should include a discussion on what we really mean by degrees of freedom in the context of phase diagram. So supposing if I take a composition over here on this line, okay, and then what I can do is I can either change the composition a little bit, but then automatically the temperature has to come down so that I continue to stay on this line and my phases don't change, or I can bring down the temperature, but then automatically, in order to stay on this line, the composition is getting changed, right? So what I'm noticing over here is I cannot simultaneously change the temperature and the composition and still stay on this liquidus line. So there is only one free variable. The other one gets decided the moment I fix the value of this variable. So this is a situation where we will say that there's only 1 degree of freedom. Now the Gibbs phase rule will give you a relation between the degrees of freedom, the number of components, the number of phases, and then you have got this 2 over here. This 2 basically represents 2 degrees of freedom. So one is temperature and one is pressure. Now for condensed system, which is basically the type of systems we'll be looking at, we are not going to vary the pressure. So this pressure contribution should not be there, and therefore the Gibbs phase rule for condensed system becomes this specific equation, that degrees of freedom equals the number of components minus the number of phases plus 1. But if you are looking at the generalized relation, it says that degrees of freedom equals number of components minus number of phases plus 2. So if we now consider this eutectic reaction, let's get back to the phase diagram so that we can appreciate this a little bit better. So I have my eutectic point over here. So at the eutectic point, the liquid and the two solids, they exist in equilibrium. If I move a little bit away from the eutectic point, now I no longer have a situation that the liquid and the two solids are existing in equilibrium, because now what's happening over here is I have moved into this L plus S1 type of region, and if I go the other side, I move into the L plus S2 type of region. Okay. So this is a situation where you cannot actually move along a line or in an area, but you are restricted to a fixed point, which we call the eutectic point. So these type of reactions, which can take place only at one point, is what we call an invariant reaction. So at invariant reaction, the degrees of freedom is going to be 0. So these are invariant points, and there are different types of invariant points. As we go over the other phase diagrams, the types of invariant points will gradually become clearer and clearer. So I'm now going to get into a very common phase diagram that people use in metallurgy, the iron cementite phase diagram. So in case of iron cementite phase diagram, you have 3 of the most common invariant reactions that you might actually see in the world of materials. The first one is a peritectic reaction. The second one is a eutectic reaction. And then the third one is a eutectoid reaction. So let us go over each of them individually. So I'm just going to zoom into this part for showing the peritectic reaction a little bit. So the part of phase diagram basically looks like this. So here you have got the delta phase, and at the top you have got the liquid phase. So this is basically liquid plus delta, and then at this stage you are having the formation of the austenite phase. So if we similarly label the phase fields over here, this phase field is going to be delta plus austenite, and then on this side you are having the austenite plus liquid. So the point over here, that is your invariant point, and at this point, according to the peritectic reaction, the liquid plus a solid will give rise to a second solid. So if you look at the composition right through the peritectic composition, you will see that the liquid plus delta is giving rise to gamma. So this is another type of invariant point. And if you look at most of the materials related phase diagrams, you will find peritectic, eutectic, and eutectoid as the most common invariant reactions. Of course, there are others, and we are going to talk about them as well. But these 3 are the most important one and the most common ones, I would say. The second one is the eutectic, and in this case, you can see that this, in case of the eutectic reaction, the liquid is giving rise to 2 solids. So one of them is right over here, the austenite, and the other is over here, which is the cementite, Fe3C. As you go below, you will see a third type of invariant reaction, which is the eutectoid reaction. The eutectoid reaction is very similar to the eutectic reaction, except that instead of a liquid phase, we actually start with a solid phase. And then the solid phase is going to go through this eutectoid point and give you 2 other solids. So S1 gives you S2 plus S3. In case of this iron cementite phase diagram, the austenite will give ferrite and the Fe3C phase. So peritectic, eutectic, eutectoid. These are the three most common types of invariant reactions that you will come across. There's another one that I wanted to bring up, and that's the peritectoid reaction. And this is not such a common reaction, not as common as the other ones, but nonetheless, you can see an example of a peritectoid reaction in case of this cobalt niobium system. So, in case of a peritectic, as opposed to the peritectoid, in case of a peritectic, you basically have a liquid and a solid giving rise to a second solid. In case of the peritectoid, you have got two solids giving rise to a third solid. In addition to this invariant reactions, you also have another phenomena which comes up in phase diagrams known as spinodal decomposition. So spinodal decomposition occurs when one solid gives rise to two solids. So alpha gives rise to alpha 1 plus alpha 2. Now this is actually a little different from your standard eutectoid type of reactions, because when you are having a eutectoid reactions, the two solids that form, they don't have the same crystal structure necessarily. Here, basically what's happening is alpha, alpha 1 and alpha 2. The crystal structures are going to be more or less identical, and the only difference is going to come in terms of the lattice parameter. So I'm not going too much into the thermodynamics of phase diagrams. I'm just trying to highlight the possibilities that can arise based on the type of phase diagram your material shows. And if you have awareness of the phase diagram your material is showing, you will be able to get a good understanding of what phases will form, and depending on what phases and in how much fraction they form, the properties of material is also going to be changing. Now, of course, in addition to all of this, it's not just the amount of a given phase and the composition of the phase. It also depends on how the phase is distributed. So whether you have the phase present as in very small sizes or the same volume but present in large size and separated by a lot of the second phase, that is going to make a major difference. And this is really where this microstructure of the material becomes important. So we will slowly get into the microstructural aspects as well, but right now let us continue with our discussion on thermodynamics and phase diagrams. So in addition to this, the type of invariant reactions we talked about, mainly your eutectic, eutectoid, peritectic, peritectoid, and other types of phase diagrams like your isomorphous phase diagram or spinodal decomposition. There are a couple of other phase diagrams in invariant reaction which we should mention briefly. So namely, they are the monotectic and the syntactic. These two types of invariant reactions are not very common. Syntactic is in fact even more rare than the monotectic. So now as we look at all of these invariant reactions and types of phase diagram, I'll just want to point out one thing, more like a mnemonic than anything. Whenever the name is ending with a "ic", it means a liquid is involved. So eutectic means a liquid gives rise to two solid. In peritectic, it's a liquid which is coming together with a solid to give a second solid. Similarly, in monotectic and syntactic, you have got liquids involved. And anytime you have got the name ending with oid, this is where the phase transformations are completely solid state. So this is just an overview of the different types of invariant reactions that are possible and the different types of phase diagrams that one encounters in materials. The main reason why we went over this is so that you know a repository from where you can pick up the phase diagrams. You know that how the thermodynamics can come together and help you compute the phase diagram. And therefore, the idea over here is if you already know what type of phase diagrams can be there, you can more effectively use the thermodynamic features to model the phase separation process that can already occur within your machine learning code. And essentially what you will be trying to do is you will try to capture things which will reflect all of these nuances as the calculated features in your data set.